we'll go to the design details of this structural model. Okay. We will design it using the ACI standard 14 and the 19 edition. Okay. And then we'll have another example. Okay, for designing a beam. So we have two examples for designing shear for slab. Okay, designing shear for beam. Okay, but before that, do you have any questions regarding the last lecture that we have did?
Nope.
Okay, so let's get started. And again, Muhammad, if you didn't understand anything, you can just stop me so we can make clear that the learning process is clear and exactly perfect for you. Okay.
Okay.
So we have this example referring to the figure 4.6. So this is the figure 4.6, which is a concrete slab for an example 4.1. Okay. The concrete, if prime C is 24, okay, this is the given value for both concrete and steel. Steel is grade 60. The slab width B is equal to 1000 millimeter or 1 meter. So this is the B, the width of the slab. As we make a section in the slab, let's assume. So we have to take a strip. This strip has a width of 1 meter, and it is thickness to be 25 centimeter, or let's say 250 millimeters. The slab effective depth D is equal to the overall thickness minus the cover. And since the cover in the slab, according to ACI code, is 40 millimeters, therefore D would be 210 millimeter. And we have support beams because this strip of the slab in the plan, if we take that strip, then it will be supported by beams, right?
Yep.
Because the beam is supported by columns, and since the beam supported by columns, by the same concept, the slab already supported by beams,
Yeah.
right? Okay, is that clear?
Yes. Yes.
Okay, so we have the beams that's supported by the slab. I mean, the slab that's supported by beams. The beams have 50 centimeters or 500 millimeters width. Now, the example is just to check the slab thickness for shear, because the thickness of the slab is very important in designing shear, because the shear forces or the shear resistance capacity for shear forces is already defined by the section property or section dimension or geometry. And if we let me just open this T section, concrete beam. Okay, let's go in any. Let's assume we have this, for example, and let's open just the image here. Now, I think it's not clear, but we can just focus on the concept. If we have this T section, you see the image, Muhammad?
Yes. Yes.
Okay, so if we focus on the concept, we have this T section, and this T section is consists of what is called the flange and web. This is the web. Okay, so we have shear forces right there. You see this is the shear force diagram. So we have these shear forces acting on this beam, and by the way, it is a section. So we are viewing a section of the section beam. Then the shear forces or the shear capacity of the section is more efficient for the part of web. The flange can resist the shear forces, but not like the efficient capacity of the web. So flange, it is more efficient for the moment capacity resistance, and on the other hand, the web has the shear forces rather than the moment capacity resistance. I hope it's clear because it is depend on the web, or what's called the flow of the shear forces. Okay, the flow of the shear forces after acting on this beam perpendicularly is transferred more in the web because the web has more capacity to resist the shear forces.
Understand. Yeah. Yes.
Thank you, Muhammad. Okay, so we have this structural model, and we see we have a cantilever, and it is 1.8 from the center of the support, and this support is a beam, and this support is another beam, right? In the third dimension, in the page, in the screen, right?
Yes.
Okay, so we have the W ultimate already defined on the slab. So we can assume now in 2D dimension that a slab is just like a simple model simple structural model for a beam. So we have this beam, for example, that has B equal 1 meter and H equal 25 centimeter, 4.25 meter, and we have W ultimate. And also the W ultimate now is 17.22 kilonewton per meter. So it's just like a beam, not 4 kilonewton meter square. Why? Because we take a strip of 1 meter.
Okay.
Is that clear?
Yes, yes.
Yeah. We didn't take, yeah. I mean, we didn't take a strip of 2 meters because we need to simplify the equations, the analysis, and so forth. So we take a strip of 1 meter. So therefore, the W ultimate will be kilonewton per meter unit length load. And also here,
Okay.
we have a point load. The ultimate is equal to 26.65 kilonewton. Assuming maybe we have, okay, in the practical field, why we have this point load? This maybe we have column, or I don't know, maybe we have a large equipment there. So we need to assume, or we need to consider that point load because it affects the analysis in the shear diagram and the moment diagram. Okay. So now we can simply have the ended shear forces. The end shear here is equal to 26.65, and here we will be less, will be large because we have here also we have an uniform load 17.22, but by 1.8. Let's open the calculator. Okay, this is 1.8 by 17.22, so it is 30.99, right? Plus
Okay.
26.65, so it is 55.64. And here also by the same way we can consider it. Here we have a reaction, and here we also have another reaction. Okay, since the load is acting downward, okay, if we assume that we don't have this support, what is the reaction direction of the support? The pin support will be upward or downward, assuming we don't have this, with assuming we have just only this support, we don't have the ruler support. Then the reaction is upward or downward there?
Reaction is upward.
Exactly. And by the same way, if we assuming that we don't have this reaction, what will be the failure mode or the reaction in this ruler support? Is upward or downward?
Still upwards.
Exactly. Therefore, we have upward here. And we can assume by this way, we have 17.22 by 6. Okay. W ultimate by L over 2. Okay. 51. It not will be like this. I mean, we need to make the equilibrium equation, but if we're assuming that we don't have this cantilever, therefore it will be W ultimate L over 2, because this is just like a simple supported. But we need to make the equilibrium equation for Fy, summation of forces in the y direction will be 0. So we have reaction in A, reaction in B upward is equal to D, 17.22 by 6. Okay. This is kilonewton per meter. By meter, it will be kilonewton, like a point load here. Downward,
Yes.
right? Plus the downward, plus also we need to consider the here the 17.22 by 1.8, which is 57.68 downward plus 26.65 downward. Then we can we can compute the reactions in A and B. Is that right? Here?
Yeah, summation of Fy, yeah, that should be right.
Exactly. Now, we need to compute the maximum ultimate shear force at a distance d from face to support. Why a distance d from face to support? You can take at exactly at the center of the support or at the face of the support. But this means that the V ultimate will be larger. And this is just like the allowance distance to take the shear. So it will be less according to ACI code. So the ACI code, told us that you can take it, the shear force, V ultimate, okay, to be at D distance from face of support. Okay, so we can take it. Okay, V ultimate, therefore, would be the larger value, and it would be in here. And that's clearly shown because we have cantilever, we have point load, we have uniform load. So the reaction will be here very large. Okay. And V ultimate therefore will be equal to the maximum ultimate shear force here. Okay, the larger value, 64.32 minus the uniform load, because we need to take it a distance d of the support, of the face of the support. So minus the W ultimate, which make the shear forces, but by distance. So this is the W ultimate. By the distance, we will minus another shear force that is just the interval between the face of support and the distance from face of support. Is that clear?
0.25, 0.21, where are they coming from?
Yes, 0.25, because we have 0.5, the beam width support, because this is the support and it is 550 or 500 millimeters. So it is,
That's the width of the beam, yes?
yeah, it's the half of the width of the beam, right? And we need to take the distance d. This is the d distance. Okay, so this is why that, because 64.32 is at the center of the support, at the center of this beam, and we need to take the V ultimate up to the d distance from the face of the beam, right? Clear? So we minus
Yes.
17.22 by the distance that we need to shift from the center, which is equal to the half of the beam, because we are in the center. So we minus the half of the beam width, so 0.25, and the 0.21, which is the d distance, right?
The effective depth?
Right, exactly.
Okay.
Is that clear?
Makes sense now.
We can explain it more if you want.
No. Now it makes sense, because we were at the center of the beam, 25 on one side and 25 on one side. So for us to come to the face of the beam, we have to come back 25. And then when we are there, we have to, that d distance, which is in the formula, we have to also add it. It makes sense, very clear, I understand.
Thank you. Perfect, I hope. Okay, so now we can compute the 5VC. And again, Muhammad, just let me know if you understand what is the term of 5VC is exactly is for me.
5VC. Is it like the concrete shear strength?
Yeah.
Is it the maximum, or is it the design VC?
No, look, we have force, or let's say we have demand and capacity. Okay.
Okay.
The capacity is 5VC. The demand is V ultimate. And once the capacity is larger than V ultimate, so it's safe. Otherwise, we need to consider that difference, okay, in our shear reinforcement.
All right.
Yes,
Makes sense.
so the difference between 5VC and V ultimate will give us the design of shear reinforcement or the shear stirrups. Okay, so we have phi, which is a reduction factor for shear strength to be 0.75. It's okay. And according to 14 edition, 318-14 shear strength capacity 5VC is given by this formula. Again, lambda is equal to 1. It depends on the type of concrete, and since it's normal concrete, then it will be 1. The root square of f prime c, we have already f prime c given. B web, which is the depth of the, the width of the structural member, in this case will be slab. So we take is as strip, so it would be 1000 millimeter. And D is the effective depth already given or computed. Therefore, already we have 5VC. And since it's equal to 128, but V ultimate at the D distance of the base of the support is equal to 56. Okay, then it is larger, then it's okay. And this is by 14 edition. Now, if you compute it by 19 edition, and this is the formula is given, and it depends on rho W. Okay, for the rho of W means the rho of the web. Okay, and this in this case it will be 1000 because the beam is not the section, it is just a rectangle section. Then we can take it as a ratio of the H over D, because we don't have now the rho W, right? We don't have the reinforcement, for the flexural reinforcement for the beam. If we have it, we can substitute it, but if we don't have it, we need to make a ratio of it. And the ratio would be the H overall H thickness over D. And we take the thickness to be the thickness of the slab. D also the effective depth of the slab. And this is 0.001. It is a factor of the shrinkage value, which is the minimum reinforcement in beams and slabs. Is that clear, Muhammad?
Okay.
And
Yes.
okay. So we have rho W already given or computed. Now prime C already given. Nu over 6 Ag plus or minus. If you remember, it depends if the member is applied for or have tension forces or tension capacity. Okay. So we can neglect it because we don't have tension in slab. I mean, it is just like a beam, and we have moment and shear. And maybe here, maybe it has some tension forces, but we need to neglect it for now.
It's negligible, yeah.
Okay. So 5VC is equal to 5.75. 0.66 is already by the formula. Lambda S to B1 and lambda to B1 also. Rho W, lambda S is equal to 1 because it is the slab thickness to be 250, right? You can refer it to the document where lambda S is given, or we can compute it by the formula. But since the slab thickness is 250, I think if the slab thickness is 250 millimeters larger or less or equal in some this range, we need to substitute lambda S to be 1. Rho W computed that, okay, if prime C is given, and we substitute Nu over 6 Ag, assuming we don't have tension, we have tension from the moment, but I mean we don't have axial tension forces. Is that clear?
Yes.
Okay, B web is already by the equation or by the example. D is already given, and once we did that, we need just to here the 1000 just for the modification of the units, because here we have megapascal, Newton millimeter square, so we need to make it kilonewton. And since it's a shear is just like any force, so it's kilonewton. And since the 5VC here, 5VC, which is the capacity, to be 65, also larger by the V ultimate. And again, by the first edition of the code, 14 edition, the 5VC also was larger than 56. But in some cases, maybe the 19 edition need to take the reinforcement of the shear because it has some points in the code that changed, okay? And also it changed in the equation that may affect the result. Maybe the section need to have the shear reinforcement, okay? And in this case, the more exact solution can be applied using the actual non-contiguous steel. Again, we substitute a ratio because we don't have the flexural reinforcement. So, I mean, the algorithm to solve like this example is just to first of all is just to compute the flexural reinforcement by the moments. Okay, just compute the flexural reinforcement of that strip or the slab or the beam or whatever it is. Then substitute the rho W, the exact rho W in the beam. Then maybe it need for um, shear reinforcement. And you may ask yourself why we add rho W in the equation. Why the 19 edition add rho W? Since rho W is a flexural reinforcement, not for shear reinforcement. The okay, so the answer here that rho W is mainly for flexural reinforcement for moments, okay, for tension that comes from moments, but also rho W has some capacity or some effects in resisting shear forces. Is that clear?
Okay.
Okay. So we will come in another example, and here are the given details. But H now for the beam is 90 centimeter. D would be 10 millimeters. And the support column here, because we have beam, we need to design a beam for shear. The column will be supported, will support the beam, right?
Yeah.
Okay. So simply supported, very simple. W ultimate, 131. Okay, 11 span structural model for the beam, and this is the interaction. Sorry, this is the shear diagram. Would be 131.7 by 11 over 2. We have reaction upward. We have reaction also upward here. So we draw the reaction, the shear diagram like this. We start from here, and since the reaction would be upward for both, because the load is downward, so we start from here, W ultimate L, which is 11 over 2. Then we need to downward in linearly because uh, we have a uniform load, so will be linearly diagrammed like this. And here at the middle, the W ultimate would be 1, or the shear force at this value would be W ultimate pi. 11 over 12, the half of 11. Did you understand me? I mean here the shear will be 0 because we are linearly decrease the shear until this point will be 0. And here, once we come here, also it will be downward because here we have WL over 2 and here also we will have WL over 2. But here we have positive, here we have negative shear. Okay, and this will be the shear diagram. If you didn't understand this, we can simply make a cut section. And by the sign convention, and this is again for the analysis material, but I am here focusing on design of the beam. I hope you understand the diagram maybe.
Yeah. I get the concept. Yeah, I get the concept. Yeah.
Okay. I just need to focus on the design again, Muhammad, and maybe we can explain it later for the shear analysis and so forth. And there are very perfect tricks to just draw the structural model, the analysis for shear moment, even torsion, very quick. Okay.
Okay.
And again, the same concept. V ultimate would be the larger value, okay, minus the W ultimate, 131.7. We need to shift to the half of the support, which is the half of the width of the support. In this case, would be this column or this column, plus the D distance, right?
Yeah.
Now, we need to compute the ultimate over phi, which is 780, because this is the ultimate, and this is the reduction factor. Increase the design, which increase the design ultimate shear force by a reduction factor equal 0.75. So it will be 780. Now, the concrete shear strength, we need to design it. But first of all, we need to compute the VC or phi VC. The VC would be by this example. Okay, this is the equation of the code 318-14 is equal to 1 over 6. Lambda is equal 1 again. It depends on P web and D. And since it's equal to 381, compare it to the V ultimate over phi. Don't compare it to V ultimate. We need to compare it to the V ultimate over phi because we need to have a reduction factor to make it as a safety factor, right? Okay, since we have here 780 and here we have 380, therefore cannot section don't have the capacity to resist shear forces. We have the difference here. So the difference here for V ultimate, we need to take it as Vs, which is equal to 398 kilonewton. Now
That's
we need
shear reinforcement to be designed.
Exactly. Now we have a limit for the maximum Vs that allowed, because if this value exceeds the Vs, we need to take it as a Vs maximum. Is equal to 2 over 3 by the square root of f prime c bwd. And since it's equal to 1500 something 27, it's less than this value, or this value is not reached or exceeds the Vs maximum, so we can design on this value. Okay? And this means
in other words,
yes, go ahead.
In other words, if the Vs max would be less than or equal to the Vs, the section we would have to increase the size, right?
Exactly. And why we take is as a Vs maximum, because for example, we don't need to take a stirrup of size 10 millimeter each, let's say 4 centimeters. Each 4 centimeters we have a stirrup, because we need to make it in the practical installation and practical field, more practical. Okay. And also
workability also, yeah.
Yes, exactly. And since also the concrete in economic side, the concrete is less cost than the steel, right?
And the steel,
yeah. So we can increase the section to make it adequate more for the shear reinforcement or shear capacity.
Okay.
Okay. Thank you for your comment. Okay. So we have the shear reinforcement here is equal to AV over S. Again, AV over S is equal to VS over FYD. T for tension. Fy is just 420, and D is the effective depth. Vs is computed, but we multiply by 1000 because we need to make the units matched in millimeter square and in Newton. AV over S, it's equal to 1.17 millimeter square over millimeter. This number, you need to have an experience with it. I mean, once you see 2 or 3 millimeters per millimeter, you say, oh, now this value is larger. It's not expected. There's something wrong. 1.17 is just the AV over S, which means the shear reinforcement distribution. As a millimeter square of what? Of the two leg, assuming we have a single stirrup. We don't have an internal stirrup to be double stirrup. Is that clear?
Can you try to sketch it, see what is happening?
Okay, for sure. Let me just open the painter. Okay, Muhammad, just let me like this. Assuming we have a beam. Okay, we have this beam. In this beam, we have here, let's draw another color. We have like there. This is the bottom steel, and also we have here top steel. Sorry. Okay, and we have stirrup in this color. Let's make it redo. We can increase the line width. Okay, it's okay. Just like this, we have a stirrup here. And this is the hook of the stirrup. Is it clear?
Yes.
So this is the stirrup. This is the first leg, this is the second leg. So these legs, assuming we have phi of equal 10 millimeter, okay, we have 10 millimeter size, then the AV is equal to 2 because we have two legs that make the shear. We have this here shear forces, this here the V ultimate, right? We draw the diagram of the shear, we have this diagram, right? So we have here V ultimate, assuming here the support, and here are another support column, and this is a beam. So here we have V ultimate, right? And here also we have another V ultimate, which is equal, and here we have distributed load, W ultimate. So V ultimate, assuming let's say it's equal to W ultimate L, assuming the span to be 6 meter. Sorry, let's make it clear, 6 meter over 2. Okay, assuming W ultimate is equal to 14, for example, 14 by 6 over 2. So we compute the V ultimate. So we have here V ultimate. Now, we also compute the VC. We compute the VC by phi. We compare it, VS, or say, to V ultimate. Sorry, this is the VC. No. V ultimate, again, V ultimate over phi, because we need to increase it as a factor of safety of reduction factor 0.75.
No, by 0.75.
Yeah, to VC. Okay. Once we did that, we estimated VS. Now this VS, we need to design it. To design it, we need to compute the AV over S. AV over S, which would equal to the V ultimate, go back, is equal to VS over FYD. VS over Fy by the effective depth, right? Now the AV over S is simply equal to, we have these two stirrups, two legs of this stirrup. Now, again, what I need to explain, if we have another stirrup right there, maybe we'll have another stirrup here. If the depth is large, assume the depth of the beam is 80 centimeters. Tamam? Okay, 80 centimeters, or like 1 meter depth. Then I need to make another stirrups, internal stirrups here. Therefore, make it zoom in, have another stirrup here. Therefore, I have two stirrups, two legs here, and another legs here, two legs here. But in simple case, I have just two legs to consider. Then, if the diameter of this stirrup is 10 millimeter, then 10 millimeters, just make it here. We have 10 millimeters diameter, square, pi. the pi value over 4 and by 2 is equal to the AV. Okay. Now the AV over a spacing. Now I can assume I have two options to assume the diameter of the stirrup. Then I can compute the spacing. Yes, I have here. This is the AV. Okay, but I need to compute the AV over S. I can assume the diameter. I assume the diameter. I can compute the S. Okay, and also another option is to compute the S is given and then estimate the diameter of the stirrup. Is that clear?
Yep.
Very clear or half clear?
No, I got it. It's either you assume the diameter to get the spacing, or you've computed the spacing, and then from that spacing you can get the diameter.
Exactly. Okay, so Vs is given, Fyd is given. I can compute the AV over S required is equal to 1.17, and this is also 1000 just for the unit matching. 1.17 millimeter square over millimeter, because it is AV millimeter square area of the two legs, assuming we have a single, we don't have a double shear stirrup, and this is the spacing per millimeter. Now this is the required, and also we need to check it along to AV over S minimum and AV over S maximum, or it's called S maximum, AV over S minimum, and AV, not AV over S maximum, here the term to be S maximum. And again, it is represented by the AV over S, simply because S is dependent on the AV and so forth. Now, AV over S minimum is the maximum of these two equations here. And every terms are clear for us, because PW, Fy is given. So we have 0.42 and 0.42 also. This is a very simple, funny chance to have the same values. But it's okay, since it's equal to 0.42, the minimum is equal to 0.42, and our value to be 1.17, so it is larger than the minimum, so it's okay. If the AV over S required or computed is less than AV over S minimum, we need to take a minimum 0.42. Okay?
Okay.
Now we compute the S maximum to be this value. Take the maximum spacing of stirrups. Okay, S maximum between the stirrups, but before that, we need to compute, we need to make sure this formula, that 1 over 3 f prime c square root of p web d, it should be, I mean, Vs we computed is 398, should be less than this value, because this is the maximum value. Again, this is the maximum value that depends on f prime c b web d, and the main r b web d, I mean the section dimensions. Again, if this equation not adequate or not, I mean this value would be less than the Vs, or the Vs would be larger than it, then this means that the section not enough, or not economic enough. So we need to increase the section dimension by the same concept as we faced here.
Okay.
Where I forget. I think in the first example we discussed, maybe here, like just here, after we check the VS maximum.
Yeah.
Okay. So for now, Muhammad, we can, again, this is the AV how we computed. Now we have, assuming 12 millimeter for the stirrup, and it's okay, no worries. But normally in the practical field, it's 8 or 10. But he take it as 12, it's okay. And we have AV, therefore, the 12 square by pi, which is 33.14 over 4, okay, by 2, because we have two legs that have the capacity to resist shear forces. Okay, then we can compute AV in millimeter square by, now, we can assume, now we have the area. We divide the area by 1.17, which is, this is the AV. If we divide the AV by the AV over S, we can compute the S right? This is the AB over S.
Yes,
And this
yes.
is the AB. Then the S is equal to 193.
193 mm, yeah.
And again, we need to check the S maximum to be the minimum of D over 2 or 405 and 600.
That's going to be 405.
Yeah, and this is from the ACI code. You can repair it to the X maximum for beam reinforcement. There are tables that specify the standards. But again, this maximum is okay. So it's okay. Perfect. But we cannot take it in practical field each 90 meter, 19 meter and 3 millimeters, 19 centimeters and 3 millimeters. Yeah, we need to approximate it to, for example, 20 centimeters or 15 centimeters.
Yeah.
Okay. So, okay. So since that, here we have an additional note. If it is required to determine the distance at which stirrups at the spacing of d over 2 can be used, use the following calculation to be done. We need to estimate the required determined distance at which stirrups at spacing d over 2. D over 2 here is equal to 40. 40 centimeters can be used. We can do these following equations. I mean, we have what's called the dense stirrup distribution, and here, and it will be ended because we have more shear here and more shear here, and in the bottom we have less shear, and you can see from the shear diagram we have zero shear in the middle, right? Yeah, and because of this, we can redistribute or have another algorithm for distribution of the stirrups rather than distribute them uniformly. Yes, we can make them dense in these regions where the shear reinforcement is larger. And since in this region, let's say at this distance from here to here, we shift x1 and x1 from the end, then we can compute them as VS and as a minimum or required or another term. And this is the methodology. I will keep it for you, but as a solution, and it's okay, but not economic, as I said, just to make the design as a final design, by the way, it would be by 12, okay, each, let's say 19
200.
or 20, make it 20 centimeters, single stirrup. But we can make it different, for example, a distance x1. And by practical field, I will let you know what x1 would be. It would be the quarter of the span. So we have span 5.5 and 5.5, so we have 12. The half of 11, I mean. So the half of 11 would be 5.5.
5.5.
Yes.
Half of that would be 2.75.
Yes. I mean, no, I'm sorry. I mean the quarter of the span, the 11. Let's open the calculator. Where's the
That's
calculator?
2.75.
Yeah, the quarter, 0.25 of 11 would be 2.75. So maybe we can take it at 2 meter and 80 centimeters from this support, okay, as the value that we determined. And here we can compute for the another shear by making interpolation because it is linearly. So we estimated the another value of V ultimate, and we make another design for this value from this point at the end of x1 to the end of this point would be also the x1 from here. So in this region, we design for V ultimate 430, and from this, for these regions and this region here, we design for 724. Is that clear? Ahmad, do you hear me? Hello, Muhammad. Okay, so I think it's perfect for now, and we can stop here. In the next lecture, we will design a beam and column for ETABS modeling, and then we will compare the design by manual design and the ETABS solution to make sure everything is good. Okay, thank you for joining this meeting today, and we will come to the second lesson, inshallah, in the next lecture in a few days. Assalamu alaikum.